So we're going to graph the sine function over the interval of negative 2 pi to 2 pi. All right. So if you remember the orientation of the sine function, something like this. Up, down, up. All right. Starting with 0 and going to whatever the period is. All right. Now, this is the ordinary sine function, so I don't really need to do the a sine bx plus c plus d, but I'm going to do it anyway. All right, so that's the general form of a sine function, similar to cosine. All right. Sine of x would be, if I were to write it in this form, 1 times the sine of 1x plus 0 plus 0. All right. And so this is how I know it's an ordinary sine function, because the c value and the d value are equal to 0, which means there's no translation. It's not going left or right or up or down. All right. But the amplitude, the a value, is equal to 1. So I would say the amplitude is equal to 1. The b value is equal to 1, which means the period, which is 2 pi divided by b, would be 2 pi divided by 1, which is 2 pi. So that means that I'm going to get one full cycle of a sine wave over a 2 pi interval. All right. So I just need to decide a reasonable length for pi, because 2 pi is going to be double that. So I can go 4 units. I can go 6 units. I'm going to go 4 units. I'm going to let pi be 4 units. 2 pi would then be 8 units. Some water here. Stave off the next coughing fit. Everything that happens in a sine wave or a cosine wave, everything important anyway, happens in quarter period intervals. So at pi over 2 and 3 pi over 2, something special is going to happen. So the sine wave starts off at the origin, increases to the maximum at the quarter wave point. All right. Now, since I'm only graphing a sine wave, I don't really have to worry about incrementing on the vertical axis. So I can go 4 units. I can go 2 units. I can go 1 unit. I'm going to go 4 units to represent a distance of 1. All right. So 1, 2, 3, 4 down would be -1. I'm going to increase to the maximum. The maximum is dictated by whatever the amplitude is. Decrease to the midline, decrease to the minimum, and then back to the midline. And that would be one cycle of a sine wave. Now, my domain says that I have to do that over a -2 pi to 2 pi interval. So I have to do the same stuff, just going in the opposite direction. So here's -pi, -2 pi. I'm just going to follow the trend in the opposite direction. So starting here, down, up, down, follow the trend, it's going to look something like that. All right. So at this location, I'll be at the minimum. Here I'll be at the midline. Here I'll be at the maximum, and then back to the midline. Yeah, the last little bit, let me fix that. All right. So that's what the sine function would look like over the -2 pi to 2 pi interval. Now, if I do it in a calculator, y equals sine of x, put it in there, and then graph it. You know, it's not going to limit it itself to the interval that's given. It's not going to limit it to the negative 2 pi to 2 pi interval, right? So I'll have to stipulate that. But I'll go to graph. Oh, I want the table. Oops. All right, so this is in increments of 4 horizontally. Every 4 units is a tick mark, but just shy of 4 is where pi would be. Just shy of 8, or a little bit more than halfway between 4 and 8 is where 2 pi would be, right? But if you go to axes, I know this is the trickiest part. Tricky is not the right word. Annoying is probably the right word. So if I go to values of x, my minimum, I'm going to let that be equal to negative 2 pi. My maximum, I'm going to let that be equal to 2 pi. At least I know it's going to graph it in the right frame. The y I'm fine with, right? So this is what it looks like in a picture perfect graphical representation. And, you can see it's not quite as good on paper, but it's got the right bits and pieces. Now for the cosine, that starts at the maximum, decreases to the minimum, and then back to the max. All right. So same structure, same ingredients, really. I could rewrite it as y equals 1 cosine 1x plus c plus 0 plus 0. The a value and the b value are still going to be 1. The c and d are still going to be 0, so I'm going to disregard those. The amplitude and the period are going to be the same as they are for the sine function. So it's really just a matter of, okay, I'm going to label it the same way, but I'm just going to start in a different location, following the same trend. So I'm going to call this pi, 2 pi, negative pi, negative 2 pi. Just making sure. Looked a little out of whack there. All right. The cosine wave starts at the maximum. So here, decreases to the midline at the quarter wave point. Quarter wave between 0 and 2 pi would be right here, pi over 2. Halfway would be pi. 3/4 would be 3 pi over 2. So it's going to decrease to the midline at pi over 2. It's going to hit its minimum at pi, back to the midline at 3 pi over 2, and then back to the max at 2 pi. So it's going to look something like that. So follow the trend going in the opposite direction, and you'll have it. And that's a cosine wave over the interval of negative 2 pi to 2 pi. So that, I don't want to say it's easy, but it's easier than if you have a phase shift or a vertical translation. So we got to tackle that now. So we're going to hop on up to page 13. And another couple of examples where you have a cosine graph, but there's something else going on. I always recommend that you start with the general form. Y equals A cosine bx plus c plus d. Match up the given function to the general form. So call this 2 cosine 1x plus 0 minus 4. All right, the c value has to be 0 because if the c value existed, there would have been a set of parentheses in the original function. That's not the case here. So that -4 must be the d value. All right. So the a is 2. The b value is 1. The c value is 0. Now it's relevant. The d value is -4. So my amplitude is whatever the absolute value is of the a value. So 2. The b value is going to help us find the period. Period is equal to 2 pi over b. So 2 pi over 1, which is 2 pi. C value is irrelevant, so it's not going to shift horizontally. It's going to shift vertically because the d value, which is the vertical translation, the VT. So we're going to shift down 4 units. All right, so what I do is I create an intermediate graph, not my final product, and then from there, I shift every point appropriately. So in this case, down. All right, so I need to go from 0 to 4 pi. So my y-axis, I know it's not really overly visible, but this is my y-axis here. So I need to account for 4 pi units in that interval. So I'm going to go, I got to get 4 pi in there. I don't want to go too crazy. Let me see if I can get away with 4 units to equal pi. 2 pi, 3 pi, 4 pi. All right, so that works. It won't always work. So you might have to do a little trial and error. But what I tend to do is just take the number of boxes I have available and divide it by, in this case, 4, because I need 4 pi to get it in there. And that usually gets me where I want to go. All right, but pi over 2 would be right here. 3 pi over 2 would be right here. All right, so the period is still 2 pi. The amplitude is now 2. So I'm gonna let 2 boxes be equal to 1 unit. I can scale the vertical axis any way that makes sense. So it might vary from person to person. All right. Since it's a cosine graph, I'm going to start at the maximum, hit the midline at the quarter-way point, midline minimum at the halfway point, midline 3/4-way point, and then back to the max. Dash curve, not my final product. You just check something, timeout. I'm not going to have enough room because we have to shift down 4 units. That's going to put me off the grid. So I'm going to bring this closer. So everything is going to get brought in closer. I don't know, this must be the witching hour or something, but the screaming baby in the apartment next door always picks this class. Maybe they don't like math. I don't know. Either that or it's like, listen, you got to understand the kid doesn't like broccoli. Like, stop trying to feed it to him at 6:30 every night on Mondays and Wednesdays. All right, so this is the intermediate graph. And I apologize about the vertical scaling. That could pose an issue. So you have to be mindful of it. And I wasn't. All right. So now what I want to do, because this is not my final product, is I want to shift every point down 4 units. So I'm going to go red for those keeping score at home. So every point gets shifted down 4 units. And then we connect this with a nice smooth curve. I lost track of things here for a sec. Hold on. Nope, one too far with this one. And this one. Oh, wait, no, 4 units. I am going down 4 units. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The whole screaming kid thing, it unfortunately, I apologize, it's probably not something you noticed until I said something, and now it's like painfully obvious. Hopefully you're not really hearing it too much, but I know my niece was a colicky baby, and so my brother would tell me all the time about how like soul crushing it is to have a baby who won't stop crying and you have no idea what the cause is. Me personally, I know when my son was very young, we brought it upon ourselves. So we didn't know that bottles had different type nipples that go on it. So they have like a very small hole so that a little bit of formula will come out, and then a bigger one, a bigger one, a bigger one. And then they have the Y slit at the top. Now, we were still giving him like the smallest one when he was ready for the Y slit. And so we'd feed him and he would drink a little bit. And then an hour later, he'd be screaming at the top of his lungs. And we're like, what's wrong with this kid? We got to call the doctor. And the doctor's like, you think you're feeding him, but you're not. So like, take care of that. You know, I don't think that that's the issue here, because this one goes off at 6 o'clock, 6:30 every 6:15, 6:30 every single night. So that's got to be, it's like the definition of colic. So anyway, high pitch hits the high notes around, you know, is it sundown? Yeah. Sun sets, hits the high note. All right, we have another cosine function here. This time we have a phase shift and a vertical translation. The A value is 1, the B value, just be careful about this. See, x over 2 is the same as 1/2 x. So the B value is actually 1/2. C is equal to pi. D is equal to -6. So my amplitude is still is 1, like an ordinary cosine function. The period, 2 pi divided by b. So 2 pi divided by 1/2. All right. Very common mistake that people make. If you take 2, forget about the pi for a second, 2 and divide it by 1/2, you're going to get 4. Right? That's a keep change flip kind of situation. All right. So this is going to be 4 pi. The phase shift, PS, negative C over B. So negative pi over 1/2. Now that negative pi can be thought of as negative 1 pi. So if you take negative 1 and divide it by 1/2, you get a result of negative 2. So negative 2 pi. The vertical translation, that's the D value, is negative 6. All right. So we're going to shift left 2 pi units. We're going to start this graph off pretty much the same way we started the last one off. 4 units to equal pi, 2 pi, 3 pi, 4 pi. All right. This graph has a vertical shift, so it's going to go down 6 units. All right. I should say shift. I'll just tuck that in there. So shifted down 6 units. All right. So I'm going to go by, for my vertical axis, I'm going to go by 1 because I need to give myself enough room to go down 6 units. All right. So my maximum of my intermediate graph is going to be 1. Now, the period is 4 pi, which means that it's going to take 4 pi radians to go 1 full cycle of this cosine wave. So the quarter way point now is actually going to be at pi. The halfway point will be at 2 pi. 3/4 way point will be at 3 pi. And the end point will be at 4 pi. So I'm going to do a quick dash curve here. Now I want to shift every single point left 2 pi units. Now by the scale, 2 pi is 8 boxes. So every single point is going to go left 8 boxes and down 6 boxes. So I'm going to start with this one here. Left 1, 2, 3, 4, 5, 6, 7, 8, and then down 1, 2, 3, 4, 5, 6. So it's going to put me there. The 3 pi, so 4 pi went to 2 pi. 3 pi will go to 1 pi. If you count boxes, that's fine. 1, 2, 3, 4, 5, 6, 7, 8. Down 1, 2, 3, 4, 5, 6, puts it right here. All right, the 2 pi, so the 2 pi, which is right here, is going to go left 1, 2, 3, 4, 5, 6, 7, 8, and down 6 from there. All right, so if we connect these with a smooth curve, it's going to look something like this. Oop, overshot the Mac. It's the shallow ones that always give me a hard time. All right, it's going to look something like that. Now, we don't have any graph here, but we need to have graph there. So we kind of have to imagine what the graph would have looked like if it went beyond 4 pi. All right. Fortunately, these points over here kind of represent that. These points are what would have happened over here. Because it's cyclical. It's a periodic function. So you could use that to kind of get a sense of where you would be going. Every 4 units, you're hitting a special point. So the next 4 units, that'll get you down to here. And then the next 4 units after that will get you over here, and you complete the circuit. Now, you could also kind of look at it and say, well, I started with low, middle, high. Well, you can't go from high to low. You can't go from the max to the min without hitting the midline along the way. So if I'm at the minimum and I'm going to go to the maximum, the next stop would be the minimum. I have to start at the, I have to stop at the midline somewhere along the way. All right. That being said, if you're really jammed up and you just need a sense of the pattern, put it in your calculator, take a look. All right. If you go to the table, so I'm going to put this function in. So this was cosine of x over 2 plus pi minus 6. So I put that in and then go to the table. Now these numbers are hideous, but these numbers aren't really relevant. What I need are numbers going from 0 to 4 pi in increments of pi. So what I'm going to do is set the interval to go from 0 to 4 pi in pi unit increments. Right? So every tick mark along the graph will be in terms of pi. Problem is, it may not be pretty. Right? But at 0, I now know that I have to go to -7. 1, 2, 3, 4, 5, 6, 7 units down. 3.14, most people recognize that. At pi, I need to go down 6 units. 1, 2, 3, 4, 5, 6. That checks out. At 2 pi, I have to go down 5 units. So 1, 2, 3, 4, 5. 3 pi, maybe it's not as easy to recognize 3 pi from its decimal, but if you know you have 0 pi, 2 pi, the next one would probably have to be 3 pi and then 4 pi. All right. So at 3 pi, you're down 6 units. Check. And at 4 pi, I'm down 7 units. That works out also. All right. So you can kind of, I don't want to say, I hate to use the word cheat, but you could use the calculator as a reference to help you figure out the result. All right. I'm just going to pause for 1 second. Just give me a minute, folks. The correct answer is I did not. But perhaps I just staved off a disastrous situation. So I'm going to continue on. We're going to talk about the secant and cosecant graph. Now, it sounds like we're going to be kind of out of the frying pan into the fire, but I can tell you that there isn't procedurally much difference between sine and cosine and the secant cosecant graphs. There's just one extra step at the end. So I'm going to match this up with the sine cosine general form. So I'm going to write this as y equals, I'll use black, a secant bx plus c plus d. All right. So we're going to actually identify the amplitude, period, phase shift, all that stuff the same way for secant that we would for cosine. All right. So, and I'll get to it in a minute, but if I match this up to secant 1x plus 0 minus 2. So the a value is 2, the b value is 1, the c value is 0, and the d value is -2. All right. So we're going to do the same thing We're going to identify the amplitude, 2, the period, 2 pi over b, which is 2 pi over 1, which is 2 pi. Phase shift is irrelevant because C value is equal to 0. The D value, which is the vertical translation, is equal to -2, and that's going to be shift down 2 units. All right, so far it seems exactly the same as a sine or a cosine graph. I want to go from 0 to 4 pi, so I'm going to do what I did before. So every 4 units I'm going to call pi. Two, 3, 4, 3 pi. 4 pi. I'm going to let one box up. Actually, do I have enough room? I don't think I do, but yeah, I'm playing with fire, so I'm just going to let one box be equal to 1 unit. All right, my amplitude is 2, so I want to go up 2 boxes and down 2 boxes. So this is the reciprocal of a cosine function. So what I'm going to do is I'm going to treat this information as if it applies to a cosine function. So I'm basically going to say, you know, pretend it's not a secant. It's not a secant function, it's a cosine function. What would I do? So I'm going to say treat as cosine, at least in the interim. All right, so I start off at the maximum point, which is 2. At the quarter wave point, now the period here is 2 pi. So the full cycle needs to be completed before I hit 2 pi or when I hit 2 pi. So I need the quarter wave points between 0 and 2 pi. So that's pi over 2, 3 pi over 2. So at the quarter wave point, I hit the midline. At the halfway point, I hit the minimum, back to the midline, back to the maximum, continue the trend. All right, so this would be an intermediate graph. Make it dashed. But I also have to shift it downward two boxes, each point 2 boxes. All right, so I'm going to do that. So down 2 boxes, we'll put it here, 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 and so on. All right. Now, if this were a cosine graph, this would be my final answer. I mean, I would make a smooth curve out of this, and then that would be my final answer. But it's not. All right. So I'm going to make another dash curve there. It's not a cosine graph. It's a secant graph. So this still is not my final answer. Now, these reciprocal graphs can get kind of messy. So just kind of bear that in mind. But it gets the job done, right? So what we're going to do is we're going to create asymptotes, vertical asymptotes, all right? Anywhere that the original cosine function was equal to 0, the secant function has to be undefined, all right? And that's the nature of the relationship. I'll just show you off on the side here. If cosine of theta is equal to 0 and secant of theta is equal to 1 over cosine, then secant of theta has to be undefined. All right, because if cosine is equal to 0, whatever the angle is, then this whole denominator has to be 0. All right. And the way that works in trig functions is if it's undefined, that means that there's a vertical asymptote, just like a rational function. All right. So what I'm going to do is anywhere that I have brain cramp, anywhere that I have an x-intercept, I'm going to make a vertical asymptote, right? Now, if you're just going back to what we were talking about before, if you're in doubt, put it in your calculator. The thing is about reciprocal functions, you just got to go into the toolbox to get it. But I can wipe this out. I could type in y equals, I want 2 secant. So to get secant, just I mentioned this last time, but I'll say it again. Secant and cosecant. You're going to go to toolbox, trigonometry. Then you're going to go to advanced. And you'll see the functions there. So I want secant. I'm going to put an x in there. And then outside the parentheses, I'm going to put a -2. And that'll be my secant function. All right. So I'm going to just create the graph. But again, I'm more concerned with where it's going to be undefined, but we'll get to that in a second. So you go to graph and you have this, it's a mess. All right. But if you look, I'll say closely at the original black curve that I have here, I have x-intercepts, and this is why we do the intermediate graph. I have x-intercepts at these locations. All right. If you look closely, I know it's kind of hard to tell. Let me go to navigate. I'm just going to kind of scooch it a little bit. It looks like there's a vertical asymptote. If we're just kind of focusing to the right of the y-axis, it looks like there's a vertical asymptote somewhere around 2, a little bit less than 2, and somewhere between 4 and 6. Pi over 2 is 1.57-ish, right? And the 3 pi over 2 is, somewhere it's in between pi and 2 pi. So it's in the neighborhood of 5 and change. All right. So what I can do before I get into my vertical shift is I can establish where my vertical asymptotes are going to be. Right. So I'm going to use hopefully a pretty pronounced color to make it a little thicker. Going to make some vertical asymptotes here and here. And here. And finally here. I'm going to adjust my window here to go from 0 to 4 pi. The y values, I guess I'm all right with. Right. So this is what we're looking at. Our final product should look something like this. All right. What we're going to do is we're going to take the red curve. And this is kind of weird, but we're going to take the reciprocal of the red curve, which means if it's opening upward, we're going to make it open downward. If it's opening downward, we're going to make it open upward. All right. So looking at my red curve here, this piece right here, I want to flip it the other way. All right, so I got to get yet another color in here. And I told you these get kind of messy. All right, so this point here, instead of going down, I want it to go up, approaching the vertical asymptote. This part of the curve here, instead of going up, I want it to go down, approaching the vertical asymptotes. Poor quality picture. This part here, instead of going down, I want it to go up, approaching the vertical asymptote. This part here, instead of going up, I want it to go down, approaching the vertical asymptotes. And this little sliver here, it's still opening down. I want it to open up. All right. Now, it's kind of hard to see with all this mess in here that this is an equivalent graph. So I'll remind you that when you're dealing with trig functions, if you're making the graph, if you have to make the graph, I mean, this is the ideal approach. You'd have a good sense of what's going on. This requires you to know something about your cosine graph, your sine graphs, potentially, and how they relate to the reciprocal functions. But if you're in a jam, you could go into the table. It's not going to give you much, but at least it'll give you the special points. So I have my special points at 0, 0, pi, -4, 2 pi, 0, 3 pi, -4, and 4 pi, 0. And then using that in conjunction with the graph, I can get a sense of where it's opening. The one thing it's not going to give me certainly would be the vertical asymptotes, all right, which is why I recommend you do it the way I'm showing you to do it. All right, I'm going to do another one. It's still a reciprocal function graph, but I'm going to show you a very slightly different approach. All right. This way involves you saving any kind of transformations, whether it's a horizontal shift or a vertical shift, until after you've created a reciprocal. All right. So, you know what? Actually, I take that back. I'm going to do it the same way because I don't want to immediately confuse the living daylights out of people by switching it up. But I'll show you an alternate technique as we go forward. All right. So this one's going from -2 pi to 2 pi. If we match this up with the general form equation, y equals a cosecant bx plus c plus d, we could pull the relevant information out. 2 cosecant 1x plus 0 minus 2. The a value is 2, b value is 1, c is 0, and d is -1. -2, sorry. I wrote it correctly, but I said it incorrectly. One of those days, I guess. It's almost like it's the class session right before spring break. I don't know. It just has that feel. Before. We're going to call before the word of the day. Before, as in the class before spring break. Or before I go too far, I should pause and talk about the word of the day, which is before. All right, so the amplitude is going to be 2. The period we get from the b value, again, same deal as before. All right, we use the b value to help us determine what the period is. So period 2 pi over b, 2 pi over 1 is 2 pi. Now we're treating this like we would a sine function. This is a reciprocal of sine. So I'm going to pretend it actually says sine and graph it. I'm going to create the intermediate graphs as if it were a sine function. All right. There's no phase shift, right? There's no left or right shift. C value is equal to 0. The vertical translation is -2. That means we're going down 2 units. Shift down 2 units. All right. Since I'm not shifting left or right, I can really take liberties when it comes to constructing my horizontal axis. You know, the increments that I'm going to use. All right. I'm going to go back to what we were doing before. Every 4 units is equal to pi. And I need to go out to -2 pi. All right. Now for the vertical axis, I have a vertical shift, but it's only a vertical shift of 2. So I'm actually going to go every 2 units, or every 2 boxes, I should say, is equal to 2 units. You can go every 1 box is 1 units. I mean, there's nothing wrong with that whatsoever. It's just I like to use the space that's available to me. It makes a nicer graph. All right. So pretending that there is no shifting, vertical or horizontal, regardless, I could create my sine graph, which would start off at the midline, hit the maximum at the quarter-way point, midline at the halfway point, minimum at the 3/4-way point, and then back to the midline. Now, a lot of folks won't do the dashing. You know, they'll just plot the points and not create the dash curve. I like to do the dash curve because I worry that I'm going to forget what points go with what. But if you can get if you can plot those points without doing the dash curve, it might make your graph look a little less busy. All right. So following the trend, I got a full sine wave here, 2 full sine waves. Now I'm shifting every point down 2 units. All right. Now, because I scaled it so that 2 units is 4 boxes, every point has to go down 4 boxes. A lot of dead air, but we have the shifted sine wave. But again, we want a cosecant graph, not a sine graph. So what I need to do is create vertical asymptotes everywhere I have an x-intercept in my unshifted graph. All right, so that's any point that's along the x-axis for that first graph that we created, that first black dashed curve. All right, so we're going to plot vertical asymptotes. You don't have to label them because there's going to be, it's periodic, so you could have many of them. Now, if it hasn't become painfully obvious, aside from the fact that these graphs get very messy, the need for alternate colors becomes more apparent. Not really a need, as much as a desire, where you're like, okay, this is getting crazy. I might want to color code it. What I recommend is when you create your final graph, because when we take a test on this is the kind of thing that you'd have to do by hand. You know, to demonstrate this skill, you'd have to show me on paper. Right. I know some of you use an app just like me. That's fine. That's ideal because you look at all the colors I have available. Right. But if you're a pencil paper person, that's alliterative, what you're going to want to do is somehow accentuate what your final graph is, because you're going to have a lot of curves and lines and points all over the place, but you need some way of letting me know what the final answer is. So recommendation, if you're just literally pencil paper, really make that last one bold, like a bold, smooth, solid curve. All right. Or you do everything in pencil, but then use a highlighter to go over your final answer. All right. Whatever it takes to draw more attention to your final answer, that's the way to go. All right. Now, going back to the red curve here, it would be opening downward. I want the reciprocal of that. So I'm going to make it open upwards, approaching the vertical asymptote. And that's the thing. And people lose sight of this all the time. A reciprocal in terms of an equation or an expression often corresponds to a physical reciprocal, right? So I'm taking, like you take cosecant, flip it over, becomes 1 over cosecant, secant, which would become cosine. But you're actually also flipping the graph, right? So I have this part of the graph here, working from left to right, this part of the graph that needs to be flipped. So I flip it. This part of the graph also needs to be flipped. So I flip it. This part of the graph needs to be flipped. So I flip it. All right. Any smooth curves in your final product, whether you're using multicolors or you're using just ordinary pencil and paper, anything that's a smooth curve, I look at as the final answer, right? Because when we make dashed curves on a graph, it's interpreted as, well, that's not really there. It's just like a placeholder. It gives you a sense of a pattern, but that's not where you're telling me the graph is. Just going back to when we did rational functions, where I'd have, something like this for a vertical asymptote, a horizontal asymptote, but then you actually have the curve. All right, this is the actual graph, these two pieces. The dashed stuff is not actually part of the graph, just represents boundaries. But I know, like looking at this, it really gets messy and it's hard to see what's going on. So if you have a highlighter, just trace over the part that you know is the final answer with a highlighter, and you'll have it. All right, it becomes a little bit more obvious what you're saying the final answer is. All right. But again, I mean, it's a god-awful mess. There's nothing pretty about it. The final graph, when you look in NumWorks, this doesn't look half bad. But it also looks like, okay, I probably screwed up because I have 5 parabolas here. Like how is this supposed to be a secant or a cosecant? That's just the way it looks. Just like a rational function had 2 disjointed graphs based off of the asymptotes, but they all made up the function. Same idea here. All right. So we'll do one more. Something with all the bells and whistles. So it's back to a secant function. Remember, that's a reciprocal of cosine. Y equals a secant Remember, we write this as 1/2 x minus pi minus 6. We indicate, sorry, that's like a weird happenstance. It occurs to me probably more than anybody else on the planet. Every now and then my 4s become A's and my A's become 4s. I don't know. So the A is 4. The B is 1/2. C is negative pi. And D is negative 6. All right, so my amplitude, 4 units, period, 2 pi over B. So 2 pi over 1/2, which is 4 pi. The phase shift. So we have a phase shift now. The PS, negative C over B, negative, the C itself is negative, so negative pi over 1/2. So that's pi over 1/2. That's going to be equal to 2 pi. If you're in doubt, pop it in. All right. So negative pi, we would say, is 1 pi. 1 divided by 1/2 is 2. So 2 pi. The vertical translation, the VT, is just whatever the D value is. So that's negative 6. Now I'm going to really have to scale this one because my amplitude is 4, which means from the x-axis, I'm going to go up and down 4 units. But then I have to also go down an additional 6. I don't have 10 units of space here. So I'm going to let each box be equal to 2 units. So I'm going to call this -2, +2. Let me just shift that a little bit. No trig pun intended. 4, 6, 8. I'll go up to 10. And then -4, -6, -8, -10. You don't have to label all of them. Just give me a sense of what the scale is. That's really all I ask. Right? It can be a little, I mean, it's already going to be a messy graph. It could be a little distracting if you label every single thing. Now, for my domain, I have to go out to 4 pi, but I also have to be prepared to shift it left and right 2 pi units. All right, so I'm going to err on the side of, in this case, we're shifting right. And we're shifting down. Right, so I'm going to err on the side of keeping the increments smaller. So you could, and since the period is 4 pi, this is going to be a pretty wide graph anyway. I'm going to let pi be 2 units. If you remember from last time, I know we don't like study every word that comes out of my mouth. Most of us anyway. I mentioned that as long as they're even increments, all right, so let pi be equal to an even number of boxes, then you're going to be okay. All right. You might end up overshooting it. You might have to erase and do it over. But if you go with an even number of boxes to represent a particular increment, in this case pi, that's going to be okay. All right. So if this were an ordinary cosine function with an amplitude of 4, I would start off at the maximum, hit the midline at the quarter-way point because the period here is 4 pi. The quarter-way point is pi. -4 at the halfway point, 0 at the 3/4-way point, and back to the maximum at the end point. All right, so this is my first intermediate graph. Now I want to shift every point right 2 pi and down 6 units. All right. If you're shifting to the right, your best bet is to start on the left. So my 4 here, well, my 0, 4 is going to go to the right 2 pi. So that's going to put it over here. And then it's going to go down 6 units from there. All right. So over to 2 pi and then down 1, 2, 3, 4, 5, 6 units. So my new point is going to be right here. Pi is going to go over to 3 pi. Pi plus 2 pi is 3 pi. And then down 6 units. So, sorry, I forgot my own scale. Eesh. So 4, so going back to the beginning here, 4 is going to go over, I was right about this part, it's going to go over to 2 pi. It's going to go down 6 units, but that's 3 boxes. So 1, 2, 3. So it puts it right there. Right? Pi is going to shift over to 3 pi and then go down 3 boxes. 2 pi is going to shift over to 4 pi and go down 1, 2. Where am I? I lost my place. Oh, no, sorry. I told you these graphs get busy. So 2 pi is right here. It's going to go over to 4 pi and go down 1, 2, 3 boxes. Oh, I missed my pi here. So 1, 2, 3. Okay. Got there eventually. So we're looking at something like this. But again, we want it to be dashed. We just have to be able to backfill in everything else, right? Because what you have to understand is this graph continues on forever. We're just only looking at it over a 0 to 4 pi interval. So this graph here would continue, continue, continue. So there are points that'll shift out of the domain, but then there are points that are starting outside of the domain that are going to shift into it. So we have to account for that too, right? So if I know that this is my lowest point, then this has to be the new midline at this location, and this has to be my new maximum. So if I use that trend, my next point would have to be over here, followed by over here. So it would have to look something like this. All right. And again, I really mean it when I say if you get jammed up, and you saw me get jammed up here, if you get jammed up, go take a look at the picture and see what the trend is supposed to look like. Now, I don't recommend putting in the secant function here, because what I'm trying to verify is that I got my cosine graph correct. Right? So that's something to bear in mind. So what I'll do is I'll put this graph in as if it were a cosine function. All right, so y equals 4 cosine x over 2 minus pi minus 6. So put that in, take a look at the picture over the right domain. Easier said than done. Maybe a little navigate. And just make sure you have the right shape. Now, it's not picture perfect, but it is the right shape. All right, increase, then decrease. Now, a minor tweak to this would be to then take your cosine and make it a secant. And one thing that these calculators will do that a lot of the other ones won't is secant. If you just type in SEC, it understands it as secant, which is kind of nice. All right. So this is what the graph should look like ultimately. So I'm looking at the reciprocal of what I have here, which is good. All right. Now, going back to that black graph, anywhere there's an x-intercept, there should be a vertical asymptote. Now, there is more to this graph because of the scaling, but it's all there. So I create my asymptotes, and then everywhere I have a red graph here, I flip it. So this one's facing down. I want it to face up, so flip it. I got a part here that's facing up. I want it to face down. And that would be my curve. And again, like I said, throw a little highlighter on it just to emphasize, and you have the appropriate graph. And again, to get it matching up with precisely what's on the calculator screen is a little tricky, but if you play around with the domains, you know, your axes, I want to go from 0 to 4 pi, confirmed. I want to go from, well, I need to go below -10. I'll go like -16 to 16. Confirm. Again, it's not perfect, but at least it shows that you have the right ingredients in the right places. So something like this. And it seems to fit what I have on paper, although it looks nicer on the calculator screen. All right. So I have thrown a lot at you. I'm going to stop the recording.